If the universe really came from nothing, then one terrifying possibility begins to emerge. What if the laws of physics are not the ultimate truth, but only the surface of something far stranger? What if space, time, matter, and even reality itself are built on rules that are incomplete, hidden, or only temporarily true? Tonight, we're diving into one of the most unsettling questions in modern science. Before we begin, please take a moment to like this video, subscribe, and share it with someone who loves cosmic mysteries. Thank you so much for being here and for spending this time with the channel. And as always, it would be lovely to know, what time is it where you are, and where in the world are you listening from now? Settle in, relax, and let us begin. Cosmology begins in a place that is not a place, at a moment that may not belong to time, with a question that seems simple only until it is examined closely. The question asks how a universe can come from nothing. It sounds almost too plain to carry the weight that has been placed upon it for centuries. Yet the deeper the question goes, the more unstable every familiar word becomes. Universe is not only a collection of stars and galaxies, it includes space itself, the stage on which matter spreads out, the distances between objects, the history of motion, the passing of time, the rules that allow atoms to hold together, the hidden fields that appear to fill even the quietest vacuum, and the constants that remain the same in every successful experiment. Nothing, by contrast, appears to mean the absence of all of that. No matter, no radiation, no fields, no laws, no dimensions, no clock, no background, no possibility of location. But once nothing is defined that strictly, the question begins to resist the language used to ask it. How can something begin where there is no where? How can it begin then where there is no then? How can a cause act if there is not yet a stage on which causes exist? The puzzle does not merely lack an answer, it threatens to remove the meaning from the question itself. Modern science does not treat that difficulty as a reason to stop. It treats it as a sign that the edge of understanding has been reached. This edge is marked by the strange honesty that appears when the most successful theories in history begin to fail in public. General relativity describes expanding space, bending light, black holes, and the growth of the cosmos on the larger scales with extraordinary success. Quantum theory describes the restless behavior of matter and energy on the smaller scales with equal success. Together they guide spacecraft, explain stars, predict particles, and account for the faint ancient glow that still fills the sky. Yet when those same frameworks are pushed backward toward the earliest imaginable state of the cosmos, they stop cooperating. Their predictions rise toward infinities, their neat boundaries dissolve. Their shared story fractures near the beginning. Physics, at its most powerful, reaches toward the origin and finds that the floor beneath its feet is no longer solid. This is where the modern mystery becomes more unsettling than the old one. It is not only that the beginning remains unknown, it is that the very tools built to explain reality seem unable to agree on what a beginning even is. In ordinary life, a beginning takes place inside time. A star begins to shine after gravity compresses gas. A planet begins to form when dust gathers in a young disk. A storm begins when pressure, temperature, and moisture shift into a certain pattern. Each event has conditions before it, and consequences after it. Cause comes first, effect follows. But the beginning of the universe does not sit comfortably inside that model, because time itself appears to belong to the thing that is beginning. If time begins with the universe, then the idea of before the universe may be as empty as a direction beyond the end of space. This comparison appears often in cosmology, because it captures the shape of the problem without pretending to solve it. Asking what comes before time may resemble asking what lies north of the North Pole. The grammar survives, but the reference fails. That strange failure has not prevented countless attempts to picture the origin anyway. Human thought keeps trying to place the universe inside a scene. A black emptiness, a silent void, a perfect darkness waiting to be disturbed. Yet every one of those images secretly contains something. Darkness assumes space. Silence assumes time. A void still behaves like a container. Even the idea of emptiness often arrives already furnished with geometry, duration, and the possibility of events. Physics has learned to be suspicious of such mental pictures. Empty space, in modern theory, is not automatically nothing. It can possess structure. It can hold fields in low-energy states. It can allow brief quantum events. It can curve. It can expand. It can carry laws. In that sense, the vacuum studied in particle physics is already a rich and active thing. It is not absolute non-existence. It is an arena with rules. This distinction matters, because many explanations that claim to describe a universe from nothing are really describing a universe from a physical vacuum, from a quantum state, or from some deeper mathematical framework that has not vanished at all. The mystery then shifts instead of disappearing. It becomes less about how something comes from nothing, and more about why anything like a lawful vacuum exists in the first place. This is the point where cosmology becomes quietly unnerving. The universe is not merely large, it is strangely well behaved. On the larger scales, it follows patterns that can be measured, mapped, and extrapolated. Distant galaxies drift away from one another in an orderly expansion. Space carries a background temperature left over from an early hot phase. Light elements appear in ratios that fit a universe once compressed into extreme density and heat. The broad outline of the Big Bang model holds because the sky itself preserves evidence of an early beginning. The cosmos does not look eternal and unchanging. It looks as if it has a history. It looks as if it has cooled. It looks as if it has unfolded from a more compact state. For decades that evidence grows stronger, not weaker. Telescopes on Earth and in orbit, from early radio surveys to missions such as COBE, WMAP, and Planck, refine the picture with increasing precision. The universe has a measurable age of roughly 13.8 billion years. It expands, it evolves, it carries scars from youth. It is not a timeless backdrop. It is an event still in progress. And yet the success of that picture only intensifies the deeper problem. An expanding universe can be traced backward to hotter and denser conditions. But that mathematical reversal does not automatically reveal an ultimate starting point in the ordinary sense. It reveals a boundary in knowledge. At very early times, matter as it is known today does not yet exist. At still earlier times, atoms are impossible, nuclei are unstable, and familiar particles move in states that demand energies far beyond anything human technology can reproduce directly. Push further back, and the known forces themselves may merge into conditions that no present theory handles completely. Push all the way to the shortest interval that current physics treats seriously, and the language of space and time begins to tremble. The origin stands there like a bright horizon that cannot be crossed with existing maps. The Big Bang, in its strongest scientific form, does not describe an explosion inside empty space. It describes the rapid early expansion of space itself from a state that is already extreme. It tells a detailed story of what happens after the universe becomes hot, dense, and dynamic. It does not yet explain why there is any universe to enter that story at all. Some of the most careful voices in science remain cautious at exactly this point. When no answer is supported, caution matters more than comfort. It is tempting to fill the silence with certainty, to replace ignorance with any explanation that feels complete. But the history of cosmology repeatedly shows that satisfying images can mislead. The Earth once seemed fixed because motion was not felt. The stars once seemed eternal because their life cycles were hidden by scale. Space once seemed empty because its subtle contents were invisible. Each time, reality turned out to be stranger and less intuitive than common sense allowed. That pattern suggests a warning. If the beginning of the universe appears impossible, the impossibility may belong less to nature than to habits of thought shaped inside a finished cosmos. Minds that arise among stable objects and flowing time may simply be poorly tuned for origins where neither stability nor time can be assumed. Still, the unease remains, because something about the universe feels too structured to have appeared without a deeper story. The laws of physics do not seem improvised from moment to moment. They show symmetry, regularity, and a precision that holds across enormous distance and time. Gravity behaves the same in remote galaxies and nearby stars. Light from ancient epochs follows the same rules measured in laboratories. Quantum processes repeat with disciplined probabilities. The constants built into those laws allow chemistry, stars, and long cosmic history. None of this proves design, intention, or any hidden agency. But it does sharpen the central mystery. If the universe emerges from nothing, then not only matter, but lawfulness itself somehow appears. Order arrives with astonishing speed. Structure exists from the beginning or very near it. The cosmos does not emerge as shapeless chaos that slowly discovers rules. It seems to begin already constrained by them. That is why the question at the heart of the universe refuses to fade. It is not simply a puzzle about the remote past. It is a challenge to the meaning of reality in the present. Every atom, every galaxy, every black hole, every living system, every measurement made by every observatory depends on a prior fact that remains hidden. Something exists. Space exists. Time flows. Laws hold. The early universe leaves traces that can be read, but the ultimate source of the script remains out of sight. Perhaps there was never a true nothing. Perhaps the word itself points to a state that cannot exist in any physically meaningful sense. Perhaps the universe grows from a deeper layer of reality that does not resemble space and time at all. Or perhaps the greatest mistake lies in assuming that physics, as it is currently known, reaches all the way down. If that assumption fails, then the deepest confidence of science becomes part of the mystery. The search for the beginning then stops being a search for a first moment and becomes something more disquieting. It becomes a search for the hidden conditions that make moments possible. The remarkable thing about the early universe is not only how violent it appears, but how much of it can be reconstructed at all. Human beings arise billions of years after the first light escapes the primordial fog on a small world circling an ordinary star, and yet they manage to sketch a sequence of events that begins in intervals so brief they barely seem to deserve the name of time. The confidence behind that reconstruction does not come from imagination alone. It comes from the sky. It comes from the present universe behaving as though it remembers its childhood. Matter is distributed in patterns that preserve old fluctuations. The background radiation still carries the afterglow of a younger cosmos. The abundance of hydrogen, helium, and traces of lithium match conditions that could only have existed when the universe was far hotter and denser than anything seen now. With every improved observation, the general picture survives. The universe expands, it cools, it thins. Going backward means heat, compression, and speed. Going backward means a reality so compressed that familiar categories stop holding together. This backward journey is often described as a timeline, though that word becomes strange almost immediately. At first, the timeline behaves well enough. a few 100,000 years after the beginning of the hot universe, electrons finally slow down enough to join atomic nuclei. Neutral atoms appear. Light, which had been trapped in a dense plasma, begins to travel freely. That ancient light still fills space today as the cosmic microwave background, stretched and cooled by expansion until it becomes a faint bath of microwaves coming from every direction. Earlier than that, for several minutes, the universe is hot enough for nuclear reactions, but cool enough for certain nuclei to survive. Protons and neutrons combine into light elements. Earlier still, in the first seconds, matter exists as a seething particle soup in which electrons, neutrinos, photons, and other particles constantly collide. These stages, though extreme, still belong to a kind of physics that can be tested indirectly. Particle accelerators cannot reproduce the full early universe, but they can probe pieces of the same behavior. Observations of the sky complete the rest. There is uncertainty, but there is also structure. Then the timeline approaches a depth where the sequence becomes almost dreamlike. Fractions of a second after the beginning of the hot phase, quarks do not remain bound inside protons and neutrons. They move in a dense fluid with gluons, the carriers of the strong interaction. Before that, the universe is hotter still, and the electromagnetic and weak interactions appear not yet fully distinct. The deeper the reconstruction goes, the more nature seems to return toward unity, as if the rich variety of later physics peels away into fewer and fewer ingredients. This gives the early universe a double character. It is chaotic in energy, but simple in composition. It is furious in activity, but almost bare in types of structure. Galaxies do not exist. Stars do not exist. Atoms do not exist. Even stable nuclei do not yet exist. What exists instead is a nearly featureless, expanding state governed by a small number of fields and forces in combinations that later reality keeps hidden. That hidden simplicity is part of what makes the beginning so difficult to grasp. In daily life, complexity seems to precede understanding. A forest is more intricate than a seedling. A city is more complicated than a village. But the cosmos appears to reverse that intuition. Its earliest accessible states may be less cluttered than the present, yet those simpler states are harder to understand because they lie closer to conditions where the very framework of explanation begins to break. The first known moments are not mysterious because too much is happening. They are mysterious because too much of what later becomes familiar has not yet separated into recognizable form. This is why early universe cosmology often feels like walking toward an ever brighter light that reveals less, not more. Clarity increases in measurement and decreases in meaning. The named epochs of the early universe are attempts to impose order on this vanishing frontier. They are not neat rooms in a building. They are labels placed on transitions that happen in unimaginably brief succession. The Planck epoch stands at the threshold. It refers to an interval so early and so extreme that current physics does not know how to describe it completely. Gravity is expected to behave quantum mechanically there, but no finished theory of quantum gravity yet commands general agreement. That fact alone is enough to make the opening of cosmic history unstable. The earliest named epoch is, in a sense, an admission of ignorance wrapped in a technical term. It signals the point beyond which the known laws no longer combine into a reliable guide. After that comes the idea of grand unification, the possibility that at sufficiently high energies some of the fundamental forces merge into a single description. This notion has long attracted theorists, because the separate forces of ordinary experience may be late products of a hotter and more symmetric beginning. Yet direct evidence remains incomplete. The mathematics is suggestive. The universe stays quiet about the rest. Then comes inflation, or at least the possibility of it, and with it the timeline becomes both clearer and more unsettling. Inflation proposes that the universe undergoes an extraordinary burst of accelerated expansion in an incredibly early instant. Not expansion in the ordinary sense of debris flying through space, but expansion of space itself, so rapid that microscopic regions are stretched to cosmic size. This idea first enters cosmology as a solution to several stubborn problems. Why is the observable universe so uniform in temperature across regions that seem never to have been in contact if expansion has proceeded at an ordinary pace from the beginning? Why does space appear so nearly flat on large scales instead of obviously curved? Why are certain exotic relics predicted by high-energy theories not seen in abundance? Inflation offers one powerful answer to all of these at once: a tiny patch, once small enough to share common conditions, expands so dramatically that it becomes the visible universe. Smoothness is no longer surprising. Flatness becomes natural. Unwanted relics are diluted away. The appeal of this idea is enormous, but so is its strangeness. Inflation does not merely add an event to the timeline. It changes the meaning of what comes before the hot Big Bang. In the older popular picture, the Big Bang is often imagined as the absolute first moment, a singular explosion from nothing. In the inflationary picture, the hot, dense universe of ordinary Big Bang cosmology becomes more like the aftermath of something earlier. At the end of inflation, the energy driving the expansion is converted into matter, antimatter, and radiation, producing the hot state from which the conventional timeline unfolds. In that sense, the Big Bang is no longer the complete beginning. It is a transition, perhaps even a consequence. The first chapter of cosmic history moves further back, into territory where observations become more indirect, and the words used to describe reality feel increasingly provisional. Yet inflation, powerful as it is, does not erase the mystery, it refines it. It makes the universe easier to understand in broad shape while making the origin of that shape more elusive. If inflation occurs, what starts it? What field drives it? Why does it end? Why does it end in a way that yields a universe like this one, with galaxies, stars, chemistry, and long-lived structure? Why do the tiny quantum fluctuations during inflation later become the seeds of all cosmic architecture? In this picture, the largest patterns in the universe may ultimately descend from microscopic fluctuations stretched across billions of light years. The galaxies then owe their existence, at least in part, to quantum uncertainty amplified by expanding space. The thought is almost too strange to hold steady. What appears solid and ancient may trace back to fluctuations that, in any ordinary setting, would be too small to matter. Cosmic structure begins not with grand design but with slight unevenness, slight randomness, slight departures from perfect smoothness. The universe requires imperfection in order to become interesting. This fact introduces a subtle anomaly into the story. Perfect uniformity would be simple, elegant, and lifeless. A cosmos with no tiny departures in density would never gather matter into stars or galaxies. It would remain a diffuse, cooling spread of particles and radiation. The very existence of structure means the early universe cannot be exactly smooth. It must contain fluctuations, but only of a certain kind and scale, too large, and the cosmos would collapse into disorder or produce a wildly irregular sky. Too small, and nothing substantial would form. Observations show that the young universe contains exactly the right level of roughness. Tiny variations imprinted in the background radiation at a level so slight they appear as minute temperature differences across the sky. Those differences later become the scaffolding of clusters, galaxies, and eventually planets. The universe is therefore not only expanding and cooling, it is fine-tuned in pattern, at least in the limited sense that its earliest irregularities sit in a narrow and fruitful range. This does not prove intention, it does deepen the puzzle. Why should the beginning be almost smooth, but not quite? As the timeline presses backward toward its earliest meaningful edge, another problem emerges. The language of sequence itself grows unreliable. It is easy to say first this, then that, then another transition. But this phrasing quietly assumes a stable underlying time through which events advance. Near the earliest intervals, that assumption may be too generous. In general relativity, time is not a universal river flowing independently of the universe. It is part of the geometry of space-time, shaped by matter and energy. In quantum theory, the status of time is different again, often treated as a background parameter rather than a fluctuating quantity like other observables. The unresolved tension between these frameworks matters most at the beginning, where density, energy, and curvature all become extreme. To narrate the first moments may therefore be to impose a later style of order on conditions that do not fully support it. The early epochs are necessary descriptions, but they may already be translations from something more alien than sequence. Still, the scientific picture holds enough coherence to be irresistible. A universe that begins hot and dense explains the retreat of galaxies, the primordial elements, and the ancient radiation field. Inflation, if it occurs, explains why that universe looks so smooth and flat while preserving the slight fluctuations needed for structure. Particle physics offers partial guidance on what kinds of matter fill the earliest plasma and how symmetries may break as temperatures fall. Piece by piece, the first tiny slices of time are transformed from pure speculation into constrained reconstruction. This is one of the greatest intellectual achievements in human history. It also leaves an exposed edge that may be more unsettling than ignorance itself. The more clearly the early universe can be described, the more sharply one sees where description stops. The first fraction of existence is not a blank wall. It is a narrowing corridor lit with increasingly precise instruments, ending at a door that no current theory can open. Behind that door may lie a deeper physics, a prehistory of the cosmos, or a realization that the words beginning and nothing have never meant what they seem to mean. The timeline remains one of science's triumphs, but its deepest value may be this: it carries understanding to the point where understanding fails and makes the failure visible. The singularity enters the story like a boundary that pretends to be an object. It is often spoken of as if it were a thing, a point of infinite density, infinite temperature, and zero size, the compressed origin of everything that later expands into stars, dust, biology, and thought. But in careful physics, the singularity is not a discovered object in the same way a planet or particle is discovered. It is what appears when an equation is pushed into a regime where the equation no longer knows how to behave. In general relativity, matter and energy shape the geometry of space-time, and space-time tells matter how to move. This relationship works with astonishing power across the known universe. It predicts the bending of light around massive bodies, the slowing of clocks in stronger gravity, the existence of black holes, and the large-scale expansion of the cosmos. Yet when the equations are run backward toward extreme compression, the curvature of space-time rises without limit. Density climbs without bound. Temperature follows. The mathematics drives itself into infinity. That infinite result is called a singularity, but the name can mislead. It sounds like a solution. Often it is a warning. Warnings of this kind matter because they reveal more than a technical inconvenience. They expose the possibility that the framework itself is incomplete. Physics has encountered infinities before, and again they have signaled that a theory has been carried beyond the domain where it can be trusted. The singularity at the beginning of the universe may therefore be less a true description of reality than a mark placed at the point where present understanding dissolves. This distinction is subtle, but it changes the emotional center of the origin story. If the singularity is real in the strongest possible sense, then the universe may begin in a state where all ordinary measures break down absolutely. If it is instead the edge of a failed model, then the beginning is hidden not by impossibility but by missing physics. In one case, reality itself becomes radically discontinuous. In the other, reality remains coherent while human description collapses. Both possibilities are unsettling, though in different ways. The trouble deepens because a singularity is not only a place where matter becomes extreme. In cosmology, it threatens the continuity of time itself. This is why the familiar urge to ask what happens before the Big Bang may become misleading. In ordinary speech, before is a harmless word. It orders breakfast before noon, winter before spring, childhood before age. Yet each use quietly assumes a flowing time that already exists. At the cosmic boundary, that assumption may fail. If time is part of space-time, and if space-time traces back to an origin where its own geometry becomes undefined, then before may simply not apply. The beginning would not be the first event inside a longer stream. It would be the edge at which the stream itself comes into existence, at least as far as current description can tell. This is what gives the singularity its eerie quality. It is not only difficult to imagine because it is dense or hot, it is difficult to imagine because it may not belong to any wider setting. It is an origin without outside context, a boundary not embedded in a larger known space of possibilities. Some cosmologists and philosophers of physics have argued precisely this point, that speaking of a time before the Big Bang may be like speaking of a location south of the South Pole. The sentence is grammatically allowed, but physical meaning drops away. Such analogies do not solve the mystery, yet they perform an important kind of cleanup. They remove a common illusion, the illusion that the universe must have started inside a pre-existing emptiness that waited there beforehand. If time begins with the Big Bang, then there is no silent cosmic room in which the beginning occurs. There is no external clock counting down to the first instant. There is no blank darkness waiting to be pierced by light. These images cling to thought because human minds are shaped inside a universe where time and space feel obvious, but cosmology keeps forcing those intuitions to retreat. The beginning may not resemble an explosion into emptiness. It may be the first appearance of the emptiness into which later things seem to be placed. And still, even when thought becomes disciplined enough to let go of the image of a pre-existing void, a different discomfort takes its place. The singularity seems almost too convenient as a limit. It explains and refuses explanation at the same moment. Run the equations backward, and they converge. Ask what this convergence means physically, and the answer becomes uncertain. This ambiguity is one reason modern cosmology no longer treats the singularity with the same confidence that earlier popular accounts sometimes suggested. The mathematical prediction remains important, but it is read more cautiously. It marks an extreme where general relativity alone should not be expected to govern reality without help from quantum principles. Gravity becomes too intense, distance is too small, and energy is too great for a classical treatment of space-time to remain complete. A quantum theory of gravity is expected to alter the picture, perhaps drastically, but expectation is not enough. The required theory remains unfinished, and without it the true status of the singularity stays unresolved. This unresolved status is part of what makes the origin of the universe feel both scientifically grounded and fundamentally open. The evidence for a hot early universe is strong. The evidence for expansion is strong. The evidence that the cosmos evolves from denser, hotter conditions is overwhelming. None of that forces reality to contain an actual singular point of infinite density. It only forces the current equations, when extrapolated without quantum correction, to behave as if such a point exists. That is a more careful and more mysterious statement. It leaves open the possibility that the beginning is not a singularity, but a transition through a state that present theory cannot yet describe. There may have been a bounce from an earlier contraction. There may have been a quantum tunneling event from a different state. There may have been a prehistory whose traces are almost entirely erased. There may have been no conventional before at all. The singularity remains central not because it is secure, but because every alternative must explain why the known universe still looks as though it emerges from an extreme beginning. Black holes make the issue even more unsettling, because they create singularities of a different kind inside the present universe. According to general relativity, matter collapsing beyond a certain point can form a region from which nothing can escape, an event horizon. Deep inside, if the equations are taken literally, collapse continues toward another singularity. This parallel matters because it suggests that singularities are not unique to cosmic beginnings. They arise whenever gravity is driven past a certain threshold in the theory. Yet black holes also reveal why singularities are suspicious. Many physicists believe that the singularity inside a black hole, like the one at the origin of the universe, is a sign that classical gravity has exceeded its authority. Quantum effects, ignored in the pure relativistic picture, should become decisive before infinities are truly reached. If that belief is correct, singularities are not physical objects waiting to be found. They are missing chapters in the theory. They are the shadows cast by an incomplete description. The universe may be hinting at this incompleteness through observation as well as theory. The cosmic microwave background, the faint relic light from the early universe, is not perfectly uniform. It carries tiny fluctuations in temperature and density across the sky. These variations are minute, but they are essential. They later grow into the structure of the universe. Their pattern is one of the great clues in modern cosmology. It reveals an early universe that is nearly smooth yet slightly uneven, nearly simple yet seeded with future complexity. Importantly, this pattern does not obviously look like the aftermath of a crude singular beginning in the naive sense. It looks more refined than that. It looks as though the early universe passes through a state that shapes fluctuations in a disciplined, statistical way, possibly through inflation, possibly through something related to quantum fields in curved space-time. The more closely the sky is measured, the more it appears that the beginning is not merely a burst of incomprehensible chaos. It is a process with structure. That structure may be impossible to explain with a bare singularity alone. This is where the mystery turns inward. If the singularity is not the final truth but the edge of failed mathematics, then the question changes from what happens at the singularity to what kind of reality replaces it. Several broad possibilities have been explored. In some approaches, space-time itself becomes quantized at the smallest scales, losing the smooth continuity assumed by general relativity. In others, quantum geometry prevents infinite compression and replaces the singularity with a bounce. In still others, the universe nucleates from a quantum state in which the classical notion of time is not yet applicable. There are models in which time behaves differently near the beginning, models in which the earliest phase is Euclidean rather than temporal in the familiar sense, and models in which the universe tunnels into existence from a condition that is not nothing but also not a pre-existing cosmos in the usual meaning. These ideas differ sharply, and none commands universal acceptance. But all of them share one quiet implication: the singularity may not be where reality begins. It may be where older language stops. That possibility has consequences beyond cosmology. If the singularity dissolves into deeper physics, then the laws that currently describe the universe may also have a history. General relativity may be emergent, valid on large scales but not fundamental. Classical space-time may be a later approximation, like temperature arising from microscopic motion. Even time itself may not be basic. It may appear only after some deeper structure settles into a regime where events can be ordered. This idea sounds radical, yet parts of modern theoretical physics keep circling toward it from different directions. Quantum entanglement, holographic ideas, and attempts to derive geometry from more abstract relationships all suggest that space-time may not be the bedrock it appears to be. The singularity then becomes a particularly dramatic place where this hidden architecture briefly shows through by causing the visible framework to fail. There is another reason the singularity remains so haunting. It stands at the intersection of knowledge and human instinct. Instinct wants an origin that behaves like all other origins, with a cause, a container, and a sequence. Knowledge keeps stripping those features away. First, the universe is found not to be eternal in its visible form. Then the beginning is found not to be an explosion in space, but the expansion of space. Then the first moment is found not to sit inside time, but to coincide with the emergence of time as currently understood. Then the singularity itself becomes suspect. No longer a clear physical point, but a signal of theoretical breakdown. Each step removes a layer of intuitive comfort. What remains is not a smaller mystery, but a cleaner one. The origin is not hidden because it is far away. It is hidden because the concepts brought to meet it transform under pressure in this sense. The singularity serves an almost paradoxical role in cosmology. It is both the oldest image of the beginning and one of the least likely to survive in its simplest form. It remains useful because it dramatizes the limit of current theories. It remains dangerous because it tempts thought into mistaking that limit for a final explanation. The universe appears to have a beginning in the sense that its observable history runs back toward a hotter and denser state. It does not follow automatically that reality begins as an actual point of infinite compression. Between those two statements lies one of the widest gaps in science. Everything known about cosmic evolution leads toward it. Nothing fully established bridges it. The singularity is therefore less like a revealed secret than like a sealed door found at the deepest level of a well-mapped structure. The corridors leading down are real. The door is real. What lies beyond is still guessed at by shape, by pressure, by faint signals slipping through the frame, but not yet seen directly. And that may be the most important thing the singularity teaches. At the point where the universe should become simplest, it instead becomes conceptually unstable. At the point where everything ought to reduce to one final description itself fragments. The earliest boundary of the cosmos is not merely a place where matter is extreme, it is where the notions of place, duration, causation, and law begin to lose their familiar form. The mystery of origin then ceases to be only a question about the past. It becomes a question about whether reality is built from ingredients more alien than space, time, and matter, and whether physics, in the form currently known, is describing the visible face of a deeper order rather than the foundation itself. The singularity does not answer how the universe comes from nothing. It does something more provocative. It suggests that both universe and nothing may be names given by late, local minds to a much stranger underlying condition that has not yet been learned to speak. Long before telescopes could see the most distant galaxies in detail, the universe was already giving away one of its deepest secrets in every direction at once. The sky is not truly dark. Behind stars, behind nebulae, behind the visible structure of the cosmos, there is a faint background glow that does not come from any ordinary object. It comes almost uniformly from everywhere. It arrives not as visible light, but as microwaves, the stretched and cooled remnant of a time when the universe is young, dense, and filled with radiation that cannot yet travel freely. This relic is the cosmic microwave background, and it is one of the strangest things ever discovered, because it behaves like a message sent from an era before stars, before galaxies, before planets, before the familiar universe becomes familiar. It is not a picture of objects. It is a picture of conditions. It is a fossil of temperature. It is a surviving imprint from when the cosmos is less than 500,000 years old, and it has transformed cosmology from a field of bold speculation into a science with an ancient sky map for evidence. The importance of this background lies first in its simplicity. It is astonishingly uniform. No matter where instruments look, the temperature is nearly the same. That alone tells an enormous story. A universe that has expanded from a hot, dense state should leave behind radiation that cools as space stretches. The background glow is exactly that kind of remainder. It fits the broader picture of cosmic expansion with almost disturbing elegance. The hotter past is not inferred from philosophy. It is still here, diluted and redshifted by billions of years of growth. When early detectors first confirmed this background in the 20th century, the result gives strong support to the Big Bang model over older, steady-state ideas. The universe has a memory. It has an early thermal phase. It is not infinitely old in the same observational sense as a cosmos that never changes. Yet the real power of the cosmic microwave background emerges only when its near uniformity is examined closely enough to find that it is not perfect. If it were perfectly smooth, cosmology would gain one mystery and lose the universe that is known today. There would be no natural seeds for later structure. Matter would remain too evenly spread for gravity to gather it into stars and galaxies. The very existence of observers, planets, and long-lived luminous systems implies that the early universe must carry tiny density variations. It does. Sensitive measurements reveal minute fluctuations in temperature across the sky. Differences so small that they seem almost absurdly fragile compared with the grand structures they eventually produce. These slight variations are the roughness from which cosmic architecture grows. They are the first visible wrinkles in an almost featureless early universe, and from them come galaxy clusters, filaments, voids, and the web-like arrangement of matter seen on the larger scales today. This is where the background radiation becomes more than evidence of a hot beginning. It becomes a coded map of the universe's initial conditions. NASA and ESCA missions, from COBE to WMAP to Planck, steadily sharpen this map. COBE first establishes that the background is astonishingly close to a perfect blackbody spectrum, the signature expected from thermal radiation in equilibrium. That result is one of the cleanest confirmations in cosmology. It means the young universe behaves with remarkable smoothness and order. WMAP later refines the pattern of fluctuations with far better precision, helping to fix core cosmological parameters with confidence. Then Planck measures the sky in even greater detail, producing perhaps the most precise portrait of the infant universe ever made. The result is both reassuring and eerie. Reassuring because the standard cosmological framework survives. Eerie because the universe turns out to be so mathematically disciplined that its early conditions can be inferred from tiny shifts in ancient microwave light spread across the whole sky. The more those fluctuations are studied, the stranger their implications become. They appear random, but not chaotic. They follow a statistical distribution close to what inflationary cosmology predicts for quantum fluctuations stretched to cosmic size. That statement compresses an extraordinary idea into a few calm words. If inflation occurs, then the seeds of galaxies may begin as microscopic quantum uncertainties in an inflation-driving field, amplified by the rapid expansion of space until they span regions larger than clusters of galaxies. In other words, the visible scaffolding of the universe may trace back to quantum noise. The larger structures in existence may descend from events that, in any ordinary setting, would remain buried in the jitter of the very small. This creates one of the most beautiful and disorienting bridges in physics. The deep cosmos and the quantum world are not separate stories. At the beginning, they may be the same story told at two scales. Even that, however, is only the clean version of the background's message. Once the main statistical pattern is accepted, attention naturally turns to departures from it. Every map of the cosmic microwave background contains not just information, but temptation. When the universe offers a nearly uniform sky with tiny structured variations, the mind begins looking for further irregularities, unusual alignments, asymmetries, hints that the standard story is not complete. Some anomalies have indeed been discussed for years. There are large-angle features in the sky that seem slightly odd, hemispheric asymmetries, unexpected alignments of certain low multipole moments, and a famously cold region sometimes called the cold spot. None of these is universally accepted as evidence of new physics. Some may be statistical accidents, some may reflect foreground complications, data treatment issues, or the ordinary tendency of minds to notice patterns in finite samples. Yet their existence matters because they keep the oldest light from becoming too obedient. The background is not only confirmation, it is also a field of unresolved whispers. The cold spot is a useful example of how cosmological mystery builds from restraint rather than drama. It is not an obviously impossible feature. It is a region in the microwave background that appears cooler than surrounding areas in a way that draws repeated attention. One possibility is that it is simply an unlikely fluctuation, rare but not forbidden. Another is that it could be influenced by a large underdense region in the later universe, a vast supervoid affecting photons as they travel through changing gravitational potentials. More speculative ideas push further, suggesting more exotic origins. None has ended the discussion. The important thing is not whether the cold spot turns out to be mundane or profound. The important thing is that the universe keeps presenting features that sit near the threshold between statistical chance and hidden mechanism. Cosmology repeatedly finds itself in that narrow band where the evidence is real, but its meaning remains open. This open meaning extends to the universe's geometry as well. The cosmic microwave background strongly suggests that space on large scales is very nearly flat. In ordinary geometry, parallel lines remain parallel, and large triangles behave according to familiar rules. In a positively curved space, the rules differ. In a negatively curved one, they differ in another direction. Measurements indicate that the observable universe sits astonishingly close to flatness. That fact is central to inflation because rapid expansion drives curvature toward near flatness. Much as a small patch on a large curved surface can appear locally smooth, without inflation or something similar, the near flatness of the universe would seem unexpectedly delicate. The early conditions would need to be arranged with extraordinary precision for the cosmos to remain so close to this balance over billions of years. Inflation does not remove the mystery entirely, but it transforms a strange coincidence into a natural outcome of a more powerful process. Yet even here, the cure is also a complication. Inflation explains flatness and smoothness by diluting earlier irregularities, but in doing so, it threatens to erase evidence of whatever comes before. The ancient sky then becomes both generous and frustrating. It tells a coherent story about the aftermath of a primordial mechanism while concealing the deeper cause of that mechanism. It is as if the universe has been cleaned by the very event that makes it intelligible. The background radiation preserves the imprint of early fluctuations. But if inflation is strong enough, It also wipes away direct signs of any pre-inflationary state from the observable cosmos. That makes the microwave background feel almost staged in its relation to mystery. It gives just enough information to make the universe seem explainable, while withholding the information needed to close the final gap. The data are rich, but they may already be post-event data, the surviving surface of a deeper drama that leaves only one discipline layer behind. This is one reason the background can feel less like a simple confirmation of theory and more like a boundary object, something that belongs partly to what is understood and partly to what is hidden. Its fluctuations encode information about matter content, expansion history, geometry, and early conditions. They also leave room for questions that no measurement has fully settled. Why these fluctuations, with this amplitude and this statistical character? Why a universe that is so smooth over enormous distances and yet just rough enough to become structured? Why an initial state so delicately poised between uniformity and fertility? Why a geometry so close to flatness? Why a sky that appears almost perfectly random within certain expectations, yet never quite free of features that provoke further scrutiny? The cosmic microwave background does not shout, it persuades, and precisely because it is so disciplined, its remaining ambiguities feel more significant, not less. There is also a deeper strangeness in the mere existence of such a signal. The universe has expanded for billions of years, built galaxies, forged stars, created black holes, and produced complex chemistry, yet still carries a detectable relic from an age before any of those later structures exist. The cosmos is not content simply to exist. It archives itself. It stores evidence in radiation, in element abundances, in the distribution of matter, in the expansion rate, in gravitational lensing, in the way galaxies cluster and evolve. This layered self-consistency is one of the strongest reasons cosmology commands scientific confidence. But it also intensifies the mystery because the universe looks more and more as though it is governed by deep, stable rules from the earliest reachable times onward. The problem is no longer to show that the cosmos has order. The problem is to understand where that order comes from, why it is so legible, and whether the legibility itself is telling only part of the truth. Some speculative ideas lean hard into the anomalies, suggesting that subtle oddities in the background may hint at collisions with other bubble universes, relic signatures of pre-Big Bang phases, or evidence that the observable cosmos is only one patch within a much larger inflationary structure. These ideas remain highly uncertain and often difficult to test cleanly. It is easy to outrun the evidence in this territory, but the evidence does at least create the space in which such possibilities can be entertained responsibly. The microwave background is not a blank screen. It is a structured relic. If there were traces of something older, stranger, or external to the visible universe. This relic light is one of the places where they might first appear, though perhaps only as slight distortions in a signal otherwise dominated by more conventional physics. The search continues partly because the background has already proved capable of carrying profound information. Once a sky map has revealed so much, it is difficult not to wonder what else it may be hiding in its faint unevenness. The oldest light therefore changes the tone of the entire origin question. The beginning is no longer a purely abstract problem. It leaves a measurable residue. It creates a pattern that can be quantified down to tiny fractions of a degree. It turns cosmology into a science of ancient conditions. But in doing so, it also reveals that the universe begins, or nearly begins, in a state that is far more orderly than naive expectation would suggest. The early cosmos is not a wild scatter of arbitrary temperatures and densities. It is almost perfectly uniform. It is geometrically balanced. It contains fluctuations that look simple enough to summarize statistically, yet potent enough to build everything later seen. The background radiation is not just a leftover signal, it is a paradox made visible. It shows a universe whose youth is astonishingly smooth and whose future depends entirely on tiny deviations from that smoothness. It confirms the broad story of the Big Bang, while sharpening the unresolved question of why the opening conditions are so suitable for a cosmos that can evolve into complexity at all. The relic glow is therefore not the end of the mystery. It is the first clear image of how elegantly the mystery is arranged. The word vacuum sounds clean, silent, and final. It suggests absence. It suggests a chamber emptied of content, a place where matter has been removed and nothing remains. In ancient thought, such emptiness already feels difficult to imagine. In modern physics, it becomes harder still, because the vacuum is not simply the absence of particles. It is the lowest accessible state of a field-filled universe, and that lowest state is not featureless. It has structure, energy, rules, and restless behavior. The more closely empty space is studied, the less it resembles nothing. It becomes a stage already occupied by invisible actors, a seeming blankness underwritten by constant activity too subtle to count as ordinary stuff and too persistent to count as true absence. This shift matters more than almost any other in the argument about cosmic origins, because many accounts that speak of a universe emerging from nothing are actually speaking about a universe emerging from a vacuum that is already far from empty in the absolute sense. Quantum theory is responsible for this change in perspective. At very small scales, the world does not settle into stillness simply because no classical object is present. Fields remain, uncertainty remains, possibilities remain. In quantum mechanics, certain pairs of properties cannot both be fixed with unlimited precision, and this lack of fixedness does not arise from poor measurement alone. It is built into the structure of the theory. The result is that a field cannot sit in a perfectly dead state in the classical sense. Even its ground state retains fluctuations. These are not fluctuations like waves on the surface of water in a material medium. They are subtle variations in the field configuration and in measurable quantities associated with it. Popular explanations often describe particles popping in and out of existence. This language is imperfect, but it points toward a real and unsettling idea. What appears empty can still host transient phenomena, correlations, and measurable effects that reveal an underlayer of activity. One of the reasons physicists take this seriously is that the vacuum is not merely a philosophical speculation, it affects experiments. The Casimir effect, for example, is often presented as evidence that even empty space has physical consequences. When conductive plates are brought very close together in vacuum, the arrangement changes the allowed modes of the electromagnetic field between them compared with outside, producing a tiny measurable force. The interpretation can be presented in different technical ways, but the larger lesson remains. The vacuum is not inert, it participates. Likewise, in quantum electrodynamics, charged particles interact with vacuum fluctuations in ways that slightly shift energy levels, contributing to effects measured with extraordinary precision. These are not decorative subtleties, they are among the most accurately tested features in physics. Empty space is active enough to leave fingerprints on matter. This is the moment where the origin question undergoes a dangerous simplification in popular thought. If the vacuum can produce fluctuations, if particles can appear briefly and vanish, then perhaps a universe can simply arise from nothing. The reasoning seems almost natural. Small things appear unbidden in quantum theory. Why not a very large thing once, under unusual conditions? Yet the leap hides several difficulties. First, the vacuum of quantum theory is not absolute nothingness. It presupposes a framework. It presupposes fields, laws, and a mathematical structure capable of supporting states, probabilities, and transitions. Second, The fleeting appearance of particle-like excitations in a quantum system is not the same as the appearance of an entire space-time with long-term dynamical history. Third, even if a universe could tunnel or fluctuate into being from some quantum vacuum state, the question would simply move one level down. Why does that vacuum exist? Why these laws? Why this structure rather than none? A quantum vacuum can be physically rich, but that richness is exactly why it cannot casually be identified with nothing. Still, the fact that the vacuum is real, measurable, and non-trivial opens a door that older cosmologies could not even describe. It becomes possible to imagine that the universe emerges not from absolute absence, but from a state with no particles, no classical matter, and no macroscopic structure, yet still governed by quantum laws. In such a picture, what appears from the perspective of later observers as the birth of a universe may be a transition within a deeper field-theoretic reality. Certain cosmological proposals use this possibility carefully. They speak not of magic, but of tunneling, instability, decay, or fluctuation in a primordial state. The vacuum, in other words, may be less like empty space in a room and more like a loaded configuration waiting for the right kind of release. That does not answer the oldest question, but it makes a different kind of beginning physically imaginable. A key part of that imagination comes from the idea that energy and matter are not wholly separate categories. Modern physics allows mass, radiation, and field energy to be transformed under the right conditions. The early universe provides the most dramatic example. In the hot, dense young cosmos, energy density is so extreme that particle-antiparticle pairs can be produced in abundance. Matter is not inserted into the scene from outside. It condenses out of the conditions present. This is one reason cosmology can sound as though it is telling a story in which everything comes from almost nothing. The universe begins in a state dominated not by formed objects but by energy, fields, symmetry, and rapidly changing conditions. Later structure then emerges as temperatures fall and symmetries break. Particles gain effective masses. Forces separate in behavior. Atoms eventually become possible. The universe, in a very real sense, differentiates itself over time. Yet none of this occurs in a true void. It occurs in a lawful setting that is already there in some form. This is what makes the vacuum simultaneously helpful and evasive. It provides a scientifically grounded alternative to the naive picture of absolute nothing. It shows that reality may contain latent structure before ordinary matter exists. But it also reveals how easy it is to smuggle assumptions into origin stories without noticing. A vacuum state already assumes mathematics, field content, and dynamical rules. It may assume space-time. In some approaches, it may assume a pre-geometric quantum state that does not yet resemble classical space-time but still has formal structure. The language changes, but the problem survives. There is always something already doing work. The vacuum becomes not an endpoint, but a refined placeholder for ignorance. It says only that the absence of particles is not the absence of physical possibility. There is another complication. Not all vacua are equal. In modern field theory, the vacuum may have multiple possible configurations, some more stable than others. A false vacuum is a metastable state, temporarily settled but not truly at the lowest possible energy. If the universe once occupies such a state, it may drive rapid expansion and later decay into a lower energy vacuum, releasing energy in the process. This picture is closely tied to inflationary cosmology. The inflationary field, whatever its exact identity may be, is often modelled as holding the early universe in a high-energy configuration that behaves like a vacuum with repulsive gravitational effects. Space then expands at an extraordinary rate. When the field rolls or decays into a lower energy state, that stored energy is converted into particles and radiation, effectively reheating the universe and launching the hot Big Bang phase. The vacuum here is not passive emptiness. It is the engine of the most important event in cosmic history after the origin itself, and perhaps part of the origin story too. Yet even this elegant mechanism raises an uncomfortable thought. If a vacuum can store immense energy while appearing empty, then emptiness is not only richer than the intuition suggests, it may be more decisive than matter in shaping reality. Stars, galaxies, and planets could then be late consequences of field configurations that exist before any of those objects take form. The visible universe would rest on invisible conditions so deep that ordinary perception never encounters them directly, in that sense. The vacuum is not merely one ingredient among many. It may be closer to the medium from which the observable cosmos differentiates. What is seen then becomes a kind of condensation, a temporary structured foam on top of deeper fields. This picture remains speculative in details, but its overall direction is already woven into successful physics. Ordinary matter is not the bedrock it once seemed. The underlying fields are prior. Dark energy makes the story stranger still. Observations of distant supernovae, supported by other cosmological measurements, indicate that the expansion of the universe is accelerating. Something in the large-scale behavior of space-time acts as though there is a persistent energy associated with empty space itself, or with a similarly diffuse component. Whatever its exact nature, this component dominates the present cosmic energy budget more than ordinary matter does. The universe is not only born from conditions where vacuum-like energy may matter enormously, it may also end under the rule of a vacuum-like component that drives ever faster separation on cosmic scales. That symmetry is haunting. Emptiness may shape both the opening and the long future of the cosmos. What appears to be absence governs history more than what appears substantial. This does not mean the mystery is solved by assigning everything to the vacuum. In some ways, it becomes sharper. The vacuum energy problem, one of the great unresolved issues in theoretical physics, highlights just how incomplete understanding remains. Naive calculations of vacuum energy in quantum field theory do not match the tiny observed value associated with cosmic acceleration in any straightforward way. The mismatch is enormous, one of the worst theoretical prediction failures in all of physics if treated too literally. This tells a troubling story. Physicists may know that the vacuum is physically real, but they do not yet know how to fit all its aspects together coherently in cosmology. The vacuum is therefore not a settled answer. It is a region of partial knowledge lit by exact local experiments and shadowed by cosmic scale confusion. All of this changes the meaning of nothing in a profound but careful way. Absolute nothing would mean no laws, no fields, no states, no structure, no geometry, no possibility. Physics has never observed such a condition, and may not even be able to formulate it rigorously. The vacuum, by contrast, is a highly structured physical condition within theory. It may contain no particles in one description, yet it still possesses measurable properties. Once this distinction is kept clearly in view, the phrase universe from nothing begins to look less like a scientific conclusion and more like a compressed headline covering several very different possibilities. Perhaps the universe emerges from a quantum vacuum. Perhaps it emerges from a false vacuum decay. Perhaps it emerges from a tunneling process out of a state with no classical space-time, but with a quantum description. Perhaps it emerges from a deeper law-like substrate that physics has only started to glimpse. None of these is the same as emergence from absolute nothingness. They are emergence from subtle somethingness that does not look like the later universe. And yet there remains a reason the vacuum matters so much to the emotional force of the origin question. It proves that the universe is under no obligation to conform to the metaphors formed in ordinary experience. In ordinary life, something comes from something visible, a house from materials, a fire from fuel, a seed from a parent plant. Quantum physics undercuts that comfort. It reveals that the boundary between existence and non-existence, between event and non-event, between object and field, is not as clean as common sense assumes. Processes can occur in states that feel almost empty. Structure can arise from instabilities. Long-term reality can descend from fluctuations that begin microscopic and indifferent. The vacuum teaches restraint. But it also teaches openness to radical possibilities. Once emptiness is found to be active, a door opens in thought that cannot easily be closed again. This is where speculative cosmology draws much of its power. If the vacuum is already a seething underlayer, then perhaps the universe does not need an external trigger in the intuitive sense. Perhaps beginnings occur when a physically allowed state becomes unstable, or when quantum possibilities resolve through processes that do not resemble everyday causation. Perhaps what later appears as a cosmic birth is, at a deeper level, a transition among states in a larger system. Such ideas remain uncertain, but they are no longer pure fantasy. They rest on a genuine scientific discovery. The closest thing physics has to emptiness is full of concealed structure. The ancient question of why there is something rather than nothing then acquires a modern complication. It may be that there was never a nothing available for reality to emerge from. The universe may stand not against a backdrop of non-being, but against a hierarchy of hidden physical states, each less obvious than the one above it, each mistaken for nothing by minds living one layer higher. If that is true, then the vacuum is not the final floor of reality. It is another surface, another apparent simplicity resting on unseen depth. That thought is quietly destabilizing, because it suggests that every time physics strips the universe down to its most elementary condition, another framework is still waiting underneath. Matter yields to atoms. Atoms yield to particles and fields. Empty space yields to vacuum structure. Vacuum structure may yet yield to something more primitive. In that case, the phrase physics could be fake begins to mean something more precise and more interesting than mere falsehood. Physics would not be fake in the sense of useless or wrong. It would be provisional, layered, and local. Its deepest concepts would describe one emergent level of reality while concealing the source from which that level itself arises. The vacuum, far from ending the argument, may be the clearest sign that the universe's apparent foundations are already one step removed from whatever the true foundation is. Inflation enters cosmology with an almost suspicious level of usefulness. It does not appear as a decorative extra attached to the Big Bang story. It appears because the ordinary hot Big Bang, successful though it is, leaves behind several deep problems that seem too precise to ignore. The early universe is nearly the same temperature in regions so widely separated across the sky that, under simple, non-inflationary expansion, they should never have exchanged information or energy. Space appears astonishingly close to flat on the larger scales, as though the total energy density of the cosmos had been set with extraordinary care at the beginning. Certain high-energy theories suggest that exotic relics might have been produced in abundance in the early universe, yet nothing like that overwhelming population is seen. The standard hot Big Bang explains the evolution of a young hot cosmos beautifully. It does not naturally explain why the starting conditions of that cosmos are so smooth, so balanced, and so selective. Inflation arrives as an answer to all of these at once, and that combination is part of what makes it both persuasive and unsettling. The basic idea is simple in outline and almost impossible in scale. Before the familiar hot Big Bang phase begins, the universe is proposed to pass through a state dominated by a nearly constant energy density, associated with a field. In general relativity, pressure contributes to gravity, and in this special situation the pressure is effectively negative in a way that causes space to expand at an accelerated rate. Not ordinary expansion, not debris moving outward through pre-existing emptiness, but space itself stretching so violently that a region far smaller than an atom can become large enough to contain everything later observed. During this interval, distances grow exponentially. Regions once in close contact are flung far apart. Any prior curvature is smoothed away. Any unwanted relics are diluted to near nothing. By the time inflation ends, the observable universe descends from a tiny patch that has been blown up to cosmic scale. The smoothness of the sky is no longer mysterious. The flatness of space is no longer delicate. The very largeness of the visible universe becomes a consequence of an early phase that acts less like an explosion and more like a sudden geometric unfolding. That is the elegant side of inflation. The more disturbing side is that it pushes the beginning backward and hides it at the same time. In the older imagination, the hot Big Bang itself is treated as the first event worth naming. Inflation changes that. The hot, dense plasma of the standard early universe becomes the aftermath of something earlier, a reheated state produced when the inflation-driving field loses its stored energy and converts it into particles and radiation. The beginning is no longer a single dramatic point from which all else follows. It becomes layered. First there is an inflationary phase or something like it. Then there is an ending of that phase, sometimes called reheating. Then the hot Big Bang unfolds in the familiar way, with particles, nuclei, atoms, radiation, stars, and galaxies. This layering should make the story richer, but it also makes the first cause harder to reach. Inflation explains why the universe looks the way it does after its earliest accessible stage, but it does not decisively explain why inflation itself begins, why it has the right properties, or whether it arises from a still deeper mechanism. In one sense, inflation is a triumph of theoretical explanation. It takes puzzles that seem disconnected and reveals them as symptoms of one missing chapter. The smooth temperature of the cosmic microwave background, the near flatness of space, and the pattern of primordial fluctuations all become natural outcomes of a brief accelerated expansion. Even more importantly, inflation predicts that the primordial density fluctuations should have certain statistical properties nearly scale invariant, close to Gaussian and adiabatic in character. Observations of the ancient sky have matched these broad expectations remarkably well. That agreement is one reason inflation remains the leading framework for the earliest moments currently accessible to observation. It does not stand on elegance alone. It stands because the universe behaves in ways that inflation led physicists to expect before the measurements became precise enough to confirm them fully. In science, that kind of success matters, and yet the closer inflation is examined, the more it begins to resemble a curtain as much as a window. Because inflation stretches a tiny region to cosmic size, it also wipes away most traces of whatever state exists before it. Any earlier irregularities are flattened and diluted. Any pre-existing structure becomes observationally inaccessible, at least within the portion of the universe that can be seen. The same mechanism that explains the large-scale order of the cosmos also deletes the evidence of its own deeper origin. This feature is not a minor inconvenience. It changes the emotional logic of cosmology. The best explanation for why the universe is so legible may also be the reason the ultimate beginning cannot be read directly. Inflation then becomes a kind of cosmic laundering process. It leaves behind a beautiful, orderly, statistically clean universe, while removing most fingerprints of the prior state from which that order emerges. This creates an unusual tension between explanation and mystery. Usually, A theory reduces mystery by connecting more facts under fewer principles. Inflation does that, but it also deepens mystery because it implies that the observable universe may be only a thin post-inflationary surface, a cleaned and expanded remnant of conditions that no current telescope can directly recover. The early cosmos then becomes like a landscape after snowfall. The shapes that remain visible are informative, but the covering is so smooth that whatever lay beneath is largely hidden. The slight irregularities visible in the microwave background are not direct fossils of a pre-inflationary world in any simple sense. They are more likely the amplified quantum fluctuations of the inflationary process itself. The universe that can be measured is therefore not the raw beginning. It is already processed through a mechanism of tremendous power. Everything known about the earliest observable structure may come after the event that matters most. This does not reduce inflation to speculation without restraint. It remains constrained by data, and many specific inflationary models have already been ruled out or disfavored by observation. The shape of the primordial fluctuation spectrum, the limits on primordial gravitational waves, and the absence of large non-Gaussian distortions all narrow the possibilities, but this narrowing creates another strange feature of the theory. Inflation may be less a single model than a family of models sharing a common qualitative mechanism. Different fields, different potentials, different reheating histories, different assumptions about initial conditions can all generate some version of inflation. That flexibility is a strength because it allows theory to adapt to measurement. It is also a weakness because the more flexible a framework becomes, the harder it can be to extract a unique, deep truth from it. Inflation may be right in spirit while many specific versions remain wrong. It may be a correct description of the observable aftermath while concealing a more radical source that no inflationary model has yet captured. Then comes eternal inflation, and the quiet mystery turns vast. In some versions of the theory, inflation does not end everywhere at once. It ends locally in patches, producing bubble-like regions where reheating occurs and hot Big Bang evolution begins, while inflation continues elsewhere. The result is a larger inflating background that keeps generating pocket universes. What is observed would then be only one local region, one bubble among many, each potentially with different properties depending on the underlying field landscape and how symmetry breaking unfolds. This is where inflation touches the multiverse, and where scientifically grounded cosmology begins to brush against ideas that feel almost too large to handle responsibly. The observable universe becomes provincial. The laws and constants seen locally may not be universal in the broader sense. They may be environmental features of one habitable patch in a much bigger structure. This possibility does not arise because cosmologists lose interest in evidence. It arises because certain mathematics of inflation seems to point in that direction, and because once inflation is treated seriously as a field process in a larger space-time, local endings need not imply a global end. But the move comes at a price. The farther cosmology goes into eternal inflation and multiverse reasoning, the harder direct testing becomes, predictions blur, selection effect enter, anthropic arguments appear. The clean connection between data and explanation, so satisfying in the standard hot Big Bang and even in ordinary inflation, becomes more fragile. One can still reason carefully in this terrain, but the mystery changes character. It is no longer only a hidden beginning. It becomes a problem of observational isolation. Even if a larger inflationary structure exists, the local universe may be causally cut off from most of it. The truth could be physically real and forever inaccessible in practice. There is a more intimate mystery as well. Inflation relies on a special state of a field that dominates the energy density of the early universe in exactly the right way. Why should such a state exist? Why should it last long enough to smooth and flatten the cosmos? but not so long that reheating never occurs? Why should its fluctuations possess the amplitude later needed to form structure without making the universe wildly uneven? Why does the field, whatever it is, behave with such cosmic usefulness? These questions are often phrased technically in terms of potentials, slow-roll conditions, and reheating parameters, but beneath the mathematics lies a simpler issue. Inflation works because the early universe is arranged to be extremely sensitive to a peculiar and productive field configuration. Whether that arrangement is natural, inevitable, or merely possible within a larger ensemble remains unclear. Inflation explains much, but it may itself depend on hidden fine-tuning or on deeper selection principles not yet understood. Some of the intrigue surrounding inflation comes from the way it transforms tiny quantum uncertainty into cosmic destiny. During inflation, fluctuations in the relevant field and in space-time itself are stretched beyond the causal horizon. Once stretched, they become effectively frozen as classical perturbations. Later, as the universe expands and cools, these perturbations re-enter the horizon and guide the distribution of matter. The galaxies are not simply late accidents in a generic expanding universe. They are downstream consequences of quantum irregularities made enormous by inflation. This chain is one of the most extraordinary in modern science. The visible architecture of the cosmos owes its existence to amplified microscopic indeterminacy. Structure begins in a whisper. Clusters, filaments, and the conditions for stars emerge from fluctuations that were once so small they belonged entirely to the quantum realm. The universe is therefore not just explained by inflation, it is haunted by it. The largest things carry the shape of the smallest uncertainties. This haunting matters because it means inflation is not only a patch for cosmological problems, it is a bridge between quantum mechanics and cosmic history. That bridge is powerful, but it may also be incomplete. If quantum fluctuations can be magnified into classical structure, then the transition between quantum possibility and classical reality becomes part of the story of the universe itself. Questions that usually sit at the foundations of quantum theory begin to echo through cosmology. What exactly counts as a fluctuation in a universe that includes all observers? What makes one branch of possible structure become the actual observed one? How does classical space-time emerge from quantum ingredients at the very moment when inflation seems to require both pictures at once? These are not objections that refute inflation. They are deeper consequences of taking it seriously. The theory may work because the universe is built on transitions between levels of reality that current language only partly describes. There is also the unresolved matter of initial conditions. Inflation is often praised because it explains the observed large-scale order of the cosmos without requiring the hot Big Bang to begin in a remarkably tuned state. But does inflation itself require special initial conditions in order to start? The answer remains contested. Some argue that inflation naturally begins under broad conditions. Others argue that the conditions needed for inflation may themselves be rare or subtle. The discussion becomes technical quickly, yet the philosophical weight is clear. A theory that solves one fine-tuning problem by relocating it to an earlier stage has not removed the mystery. It has deepened the timeline and possibly refined the kind of tuning involved, but the demand for explanation remains. Inflation may turn a puzzling hot beginning into the outcome of a prior dynamical phase, while still leaving unanswered why that phase is available at all. Even if inflation is fully real, the observable universe may therefore be a special kind of remnant, not the untouched beginning, not the whole of existence, but a region whose visible simplicity is the product of radical early expansion and information loss. That possibility changes the tone of every cosmological observation. The microwave background, the distribution of galaxies, the near flatness of space, the weakness of primordial irregularities, all become less like direct photographs of the ultimate origin and more like the polished surface left by a mechanism that has cleaned the scene. The true prehistory may exist, but inflation has made it difficult to retrieve. Physics then confronts a bitterly elegant possibility. The universe becomes understandable precisely because it has forgotten so much of what came before. If that is the case, then inflation occupies a peculiar place in the narrative of reality. It is the theory that rescues order from coincidence, connects quantum fluctuations to galaxies, and explains why the cosmos appears so smooth and geometrically balanced. It is also the theory that may prevent direct access to the deeper state from which the visible universe emerges. In one direction it is explanatory, in the other it is censoring. It makes the universe more coherent and more inaccessible at once. That dual role is why inflation feels less like a final answer than like a magnificent intermediate truth, one powerful enough to reorganize cosmology and yet perhaps destined to be absorbed into a wider picture in which even inflation is only a surface process. The universe may not begin with the Big Bang in the old sense. It may not even begin with inflation in the deepest sense, but if inflation is real, then the cosmos as it is known now starts with an erasure, and everything seen afterward may be the orderly consequence of an early event, whose greatest achievement is that it leaves almost no clear record of itself beyond the fact that it happened. Even if inflation succeeds, even if the hot Big Bang unfolds exactly as the best models describe, even if the early fluctuations in the microwave background are measured with exquisite precision and matched to the predictions of expanding space, one question remains untouched beneath all the others. Why are there laws at all? Not merely why does matter behave in a certain way once it exists, but why does reality arrive already governed? Why is there a dependable structure beneath every observation? A framework so regular that stars ignite by the same nuclear rules in distant galaxies. Atoms share the same quantum architecture across cosmic time, and space-time follows consistent geometric responses to mass and energy. The visible universe does not look improvised. It looks constrained from the beginning. It looks lawful before it looks populated. This is easy to overlook because science is built on regularity, and what is always present tends to disappear into the background of thought. But once the origin question is pushed far enough, law itself stops being the silent stage and becomes part of the mystery. The early universe makes this problem impossible to ignore. Long before stars form, before chemistry becomes rich, before any structure capable of reflection exists, the cosmos already behaves according to fixed relationships. Expansion follows precise equations. Light elements emerge in ratios controlled by stable interactions. Tiny primordial fluctuations grow under gravity in lawful ways. The microwave background carries patterns that can be statistically described with extraordinary discipline. None of this proves that the laws of physics are eternal in any absolute sense. It does show that they are already active at the earliest observationally accessible times. The universe does not first exist as a formless raw fact and later acquire rules. It appears on stage with rules already operating. If matter comes from earlier field conditions, and fields arise from a deeper theoretical framework, then the mystery is displaced again. Why this framework? Why these symmetries? Why these constants? Why not another set, or none that allow long-lived complexity at all? The constants of nature sharpen this unease. Gravity has a definite strength. The electromagnetic interaction couples with a certain intensity. The masses of elementary particles fall within narrow ranges. The cosmological parameters governing expansion and matter content take specific values. Change some of these significantly, and the later universe becomes radically different. Stars may burn too quickly or not form stably. Chemistry may lose its richness. Structure may fail to gather or may collapse too violently. The point is not to claim that life is the purpose of the universe, nor to overstate fine-tuning in simplistic ways. The point is more restrained and more haunting. The cosmos seems to depend on a delicate architecture of quantities that do not announce where they come from. Physics can measure them. It can build models around them. It can sometimes relate them through deeper theories. But the deepest why often remains unanswered. The laws appear less like derived necessities and more like given conditions whose ultimate source is hidden. This hidden source becomes especially strange when symmetry enters the story. Much of modern physics is built on symmetry principles, structured invariances that determine which interactions are allowed and how fields behave. Symmetry is one of the great engines of explanation because it compresses complexity into elegant constraints. The laws are not arbitrary collections of disconnected rules. They often arise from deeper requirements of invariance. Yet symmetry does not abolish the mystery of law. It refines it. One can always ask why those symmetries exist, why they break in particular ways, and why the universe chooses one vacuum state over another. In the early cosmos, as temperatures fall, symmetries may break and produce the differentiated world of later particles and forces. This sounds explanatory, and it is, but it also suggests that the visible laws may be frozen outcomes of deeper transitions. The universe then becomes something like a cooled remnant whose stable rules are not fundamental truths in isolation, but low-energy expressions of a prior structure that no longer appears directly. If that is correct, then what is usually called the laws of physics may already be emergent. They may hold within the observable universe the way the laws of fluid flow hold within water, real, predictive, and powerful, but not ultimate. A fluid equation does not lie simply because molecules exist beneath it. It describes a level of reality with great success while depending on a deeper substrate. The same may be true of space-time geometry, quantum fields, and even the symmetries that seem so foundational now. There are hints of this possibility across several areas of theoretical physics. Condensed matter systems show how collective behavior can generate effective particles, broken symmetries, and robust rules that are invisible at the microscopic level. Thermodynamics emerges from statistics, elasticity emerges from atomic lattices, temperature emerges from motion. Again and again, reality presents orderly descriptions that are true without being final. Cosmology cannot help wondering whether the entire visible universe lives inside a similar hierarchy. This is where the phrase physics could be fake begins to acquire its most serious meaning. It does not mean that experiments are false or that gravity fails tomorrow. It means that what appears fundamental may be the reliable surface behavior of a deeper system, much as a shadow can preserve the shape of an object without revealing its inner structure. The laws known now might be local regularities arising from a hidden layer that does not resemble particles in space and time at all. They could be like the rules of a game discovered by someone trapped inside the board, precise enough to describe every permitted move while giving no direct access to the process that created the board or selected the rules. This idea remains speculative, but not empty. Every advance toward more unified theory has already taught that the obvious furniture of reality is not ultimate. Solid objects give way to atoms. Atoms give way to nuclei and electrons. Nuclei give way to quarks and gluons. Forces merge under extreme conditions. Space and time themselves bend, stretch, and perhaps emerge. The direction of discovery has consistently moved away from appearances toward deeper relational structures. One of the more intriguing signs that law may not be basic is the relationship between information and physics. Black hole thermodynamics, quantum entanglement, and holographic ideas all suggest that geometry, gravity, and information may be more intimately connected than earlier physics imagined. A black hole is not merely a trap from which light cannot escape. It also behaves as a thermodynamic object with entropy and temperature, as if space-time itself carries microscopic degrees of freedom not visible in the classical description. The area of a horizon seems tied to informational content in a way that feels less like traditional mechanics and more like a clue that space-time is built from something statistical beneath it. In some theoretical approaches, the geometry of a region can be related to patterns of entanglement in an underlying quantum system. If that line of thought is even partly right, then space may not be the container of information. It may be a consequence of information arranged in a certain way. Law then becomes not the command issued inside reality, but the emergent grammar of a more primitive network. This possibility has profound consequences for the origin problem. If space-time emerges, then the question of where the universe begins inside space-time may be misframed from the start. The true beginning would not be the first moment on a cosmic clock. It would be the transition by which whatever underlies space-time enters a regime where time, geometry, and effective law become meaningful. In that case, asking why the laws hold might be like asking why crystallized ice has rigid symmetry while ignoring the molecular processes that produce the crystal. The laws would still matter, but as phase properties of a larger reality. The universe would be lawful because it has settled into a particular emergent state, not because eternal equations float independently in some abstract void waiting to govern it. This remains uncertain, but it offers one of the few ways to make the existence of law feel less miraculous without reducing it to brute fact. The brute fact option, however, never fully disappears. It may be that the laws simply are what they are, with no deeper explanation available or even meaningful. Many physicists are willing to accept this possibility at least provisionally, because science is not obligated to answer every metaphysical why. It is built to discover patterns, make predictions, and connect phenomena. Still, the history of physics makes brute acceptance feel temporary rather than final. Time and again, constants once taken as fixed have been folded into wider frameworks, and rules once treated as separate have been unified. Electricity and magnetism merge. Space and time merge. Mass and energy become exchangeable aspects of a deeper description. The recurring lesson is that what looks disconnected from one level often belongs to a larger order at the next. That habit of discovery does not prove that every law can be explained. It does make the unexplained status of law feel more like an invitation than a resting place. Cosmology gives that invitation unusual force, because the universe as a whole cannot be compared with an external sample. In laboratory science, if one system behaves oddly, another can be built, varied, tested, and contrasted. With the cosmos, there is only one observable instance. The laws are not just the rules within a system. They define the system's very possibility. This is why origin questions become so difficult. The ordinary scientific move of comparing different realizations is mostly unavailable. If there are other universes with different laws, they are not directly accessible. If there was a pre-cosmic phase with other effective rules, inflation may have hidden it. If the laws evolve with scale or emerge from deeper informational structures, the transition occurs at precisely the boundary where current theory is weakest. The universe therefore keeps its foundational regularities in view by showing their effects everywhere, while keeping their source out of reach. There is also a subtle emotional force in the fact that law seems older than matter. The first stars do not invent gravity. The first atoms do not invent quantum behavior. The first galaxies do not invent space-time curvature. These things are already operating in the background, directing the formation of structure long before any familiar object arrives. In a calm sense, the universe behaves as though it knows how to become itself. That impression should not be turned into intention or agency. It should be left as what it is, an observation that cosmic order precedes cosmic complexity. The equations come first, at least in every accessible description. But if they come first, they also become suspect. Anything that foundational may either be genuinely basic or the most polished illusion of all, a stable interface rather than the machinery underneath. Some of the boldest theoretical work therefore circles around the same unsettling possibility from different angles. Perhaps gravity is emergent, a thermodynamic or entropic phenomenon arising from deeper microscopic relations. Perhaps space-time geometry is encoded holographically on lower dimensional boundaries. Perhaps quantum mechanics itself is not final, but an effective statistical rule derived from a more primitive, deterministic or relational substratum. These proposals remain contested and incomplete. Yet what matters here is their shared direction. They do not merely seek to extend physics, they seek to demote it from ultimate status without reducing its power. The familiar laws would remain valid where they work, but their authority would be local to one layer of description. In that case, the origin of the universe is not just the origin of matter and space, it is the origin of the regime in which the laws now known become active and visible. If so, then the oldest cosmological mystery may have been disguised by success. Physics works so well that it invites the belief that it must be fundamental all the way down. But perhaps its greatest triumphs belong to the middle distance. Perhaps it describes the universe after the decisive emergence has already taken place. The earliest observable cosmos then would not be the bottom floor of reality, only the earliest level at which current law becomes legible. Beneath that level there may be no particles, no fields in the usual sense, perhaps not even time. There may instead be a hidden order from which laws, constants, and geometry condense together. The universe would still be real. The equations would still predict. The stars would still burn. Yet the source of law would lie outside the law's own language, and the observable cosmos would be revealed as a stable appearance resting on something stranger and quieter than any of its contents. The question would no longer be merely how something comes from nothing. It would become why law emerges from whatever is deeper than both something and nothing, and why that emergence yields a universe so orderly that it can mistake its own surface rules for the foundation of reality. Once the possibility of emergent law is taken seriously, the ground beneath ordinary reality begins to shift in a more radical way. It is one thing to imagine that certain constants might be environmental, or that the forces known today could descend from deeper symmetries hidden at higher energy. It is something else entirely to imagine that space itself is not fundamental, that time is not an eternal river, and that gravity may not be a primary interaction in the way earlier generations assumed. Yet modern theoretical physics keeps drifting toward exactly this territory, not with uniform agreement, and not with final answers, but with enough repeated pressure from different directions that the old picture of reality as matter, moving through a pre-existing geometric stage, grows harder to preserve. What had seemed like the deepest layer begins to look instead like a very successful surface. The idea of emergence already has countless precedents in science. Wetness is real, but no single molecule is wet. Temperature is real, but no atom carries a miniature thermometer. A hurricane has structure and force, yet it is not an extra object added to air and water. It is a large-scale pattern that arises from the coordinated behavior of smaller elements. A crystal appears rigid and orderly, but its visible shape depends on microscopic arrangements that do not resemble the final crystal in any obvious way when considered one by one. These examples matter because they teach a specific lesson. A phenomenon can be fully real, measurable, and predictive without being fundamental. It can obey laws of its own while resting on a substrate that behaves according to different principles. If that lesson applies to the cosmos itself, then the familiar universe may be less like a finished thing and more like a stable phase of a deeper process. Gravity is one of the first great candidates for this demotion. General relativity remains magnificent. It describes black holes, gravitational lensing, cosmic expansion, and the dynamics of large structures with extraordinary accuracy. But its very elegance can be deceptive. The theory treats gravity not as a force transmitted through space in the old Newtonian sense, but as the curvature of space-time. Massive and energetic things tell space-time how to bend, and the bent geometry tells matter and light how to move. This picture is so natural within relativity that it becomes easy to forget how strange it really is. Geometry is no longer a passive container. It becomes active, dynamic, and responsive. Yet that success leaves open a deeper question. Why should space-time geometry behave thermodynamically in some contexts, such as at black hole horizons? Why should the equations of gravity show surprising links to entropy, temperature, and information? Why should the smooth geometry of a region appear to know about microscopic counts that the classical theory does not display? These are not random curiosities. They hint that gravity may be the large-scale statistical behavior of something more primitive. Black holes sharpen that hint almost to a blade. A black hole is defined classically by an event horizon, a boundary beyond which escape is impossible. But once quantum theory enters the picture, black holes are found not to be completely black. They radiate, they carry temperature, they possess entropy proportional to the area of their horizon. This is one of the most startling results in modern theoretical physics because it binds together gravity, thermodynamics, and quantum mechanics in a single object. An apparently geometric boundary begins behaving as though it encodes microscopic information. The horizon ceases to be merely a curve in space-time. It starts to resemble the boundary of a system with hidden internal degrees of freedom. That suggestion has driven decades of thought, because it implies that space-time geometry may be more like a thermodynamic state than an eternal backdrop. Just as heat reveals the collective behavior of molecules, gravity may reveal the collective behavior of ingredients not yet fully identified. From there, the path leads naturally toward information. The universe increasingly appears to care about information in ways that older physics never anticipated. Quantum entanglement shows that separated systems can share correlations that cannot be explained by ordinary local hidden properties. Black hole information puzzles raise the question of whether information can truly be destroyed by gravitational collapse. Holographic ideas suggest that the full description of a volume of space may in some circumstances be encoded on its boundary, with one fewer spatial dimension than naive intuition would expect. This is not a poetic metaphor. In specific theoretical settings, especially in work related to string theory and quantum gravity, such dualities can be made mathematically precise. A higher dimensional gravitational system can correspond to a lower dimensional non-gravitational quantum system. The relationship is so exact in those settings that geometry itself begins to look like a translation of something more abstract. Space may not be the primary fact. It may be the readable version of deeper informational order. If that is even approximately true beyond specialized models, then the origin of the universe becomes almost unrecognizable in ordinary terms. One no longer asks what happens at the first point in space or the first instant of time. One asks how a regime capable of supporting points and instants emerges from a more primitive network of relations. The beginning of the universe then would not be the first tick of a cosmic clock. It would be the phase transition by which clock-like ordering becomes meaningful. Time might not exist in the deepest description in the way it is experienced now. It could arise only when the underlying system enters a sufficiently classical, coarse-grained, and stable condition. What feels like a flowing sequence of moments could be, at bottom, the large-scale behavior of a deeper atemporal structure. This does not make time unreal in the shallow sense. It makes time emergent, which is a much stranger possibility because it means the most intimate feature of experience belongs to the world of appearances rather than to the bedrock beneath it. There are several routes by which theorists have tried to imagine such emergence. Some approaches suggest that space-time geometry is built from quantum entanglement patterns, with distance itself reflecting the strength and structure of correlations. In that picture, things are near each other not because they sit in a pre-existing space, but because the underlying network ties them together strongly enough that geometry later interprets them as nearby. Other approaches treat space-time as arising from discrete quantum elements, tiny combinatorial building blocks that do not individually resemble a smooth manifold, but can collectively approximate one under suitable conditions. Still others explore the idea that classical space-time is the effective description of more abstract quantum amplitudes, histories, or algebraic structures. These programs differ in detail and status, but they agree on a core suspicion: the smooth space-time in which galaxies move and clocks tick may be no more fundamental than a wave on the surface of water is fundamental to the molecules below. This possibility pulls the origin question away from the old argument over something and nothing and toward a more elusive contrast between levels of reality. Suppose the universe does not emerge from nothing in the absolute sense. Suppose instead that the observable cosmos emerges from a deeper domain that is not spatial, not temporal, and not material in the everyday meaning of those words, but still physically real in a broader sense. Then the birth of the universe would resemble the condensation of an interface. What comes into being first is not matter inside space. It is the very framework that later allows matter, space, and time to appear as stable concepts. The Big Bang, inflation, and early field dynamics would then all take place after the decisive event has already happened. They would belong to the first chapter of the emergent universe, not to the ultimate origin of reality itself. This would explain why current physics describes those stages so well while failing at the final boundary. The theories were never built to reach beneath the emergence of their own stage. The language of phase transitions helps make this less abstract. Water can exist as vapor, liquid, or ice. The same basic constituents produce radically different large-scale behaviors depending on temperature and pressure. A gas does not merely contain more energetic particles than a crystal. It inhabits a different regime with different effective properties and laws. If reality behaves similarly at the deepest scale, then space-time may be one phase among others, not an all-purpose container that exists regardless of state. The early universe would then not simply be a hotter version of the present cosmos. It might have passed through a transition in which the very meaning of geometry changes. Before that transition, there may be no meaningful distance, no definite causal order, perhaps no distinction between inside and outside. After it, a classical-like space-time appears, and with it come the laws that later observers mistake for primordial truths. The universe then is not born into space. Space is born into the universe. Such a view has a strange way of preserving the success of physics while quietly undercutting its apparent absoluteness. General relativity would remain accurate where smooth space-time exists. Quantum field theory would remain accurate where particles and fields behave in their usual domains. Cosmology would still correctly reconstruct the hot, dense, early universe after emergence. Nothing in the observed record would be discarded. Yet the framework surrounding those successes would change completely. The laws now known would become effective descriptions of an emergent phase. They would be true in the same sense that the laws of elasticity are true for solids, deeply useful yet silent about the ultimate substrate. Physics would not be false. It would be incomplete at the deepest ontological level, describing the rules of the visible phase while remaining mostly blind to the generative process that brings that phase into existence. There is a reason this possibility exerts such force on the imagination. It explains a pattern that otherwise seems almost too consistent to ignore. Again and again, what appears fundamental turns out to be derivative. The Earth is not the centre. The Sun is not the centre. Ordinary matter is not the dominant content of the cosmos. Empty space is not empty. Classical certainty is not the foundation of physical behaviour. The visible object is not the elementary unit. The field replaces the particle. Then perhaps information replaces the field, and beneath information there may lie something even harder to picture. Every layer that seems final becomes provisional once a deeper one is reached. Emergent space-time would be the continuation of that trend on the largest possible scale. It would mean the universe's stage is no more ultimate than the actors crossing it. Even the arrow of time may belong to this emergent order rather than to the deepest layer. In ordinary experience, time has direction. Entropy increases. Memories accumulate of what is called the past, not of what is called the future. Stars burn their fuel. Structures age. The universe expands from a smoother early state toward greater overall entropy. But if time is emergent, then this directional flow may itself be a large-scale feature of one cosmic phase. The low entropy condition of the early universe, one of the most mysterious facts in physics, may not be a brute initial gift. It may be tied to the way space-time crystallizes out of a deeper regime. The arrow of time could then be a signature of emergence, not merely a parameter set at the beginning. This idea remains speculative, but it would connect several enduring puzzles at once: why the universe begins in an ordered state, why time has a direction, and why cosmological history unfolds as a one-way process from smoothness to structure. Of course, caution remains necessary. Emergence can become a fashionable label if used too freely, a way of replacing one mystery with a vague promise of deeper mechanism. The hard question is always the same: what exactly emerges from what, and by what rules? No consensus answer exists. Some programs are mathematically rich but experimentally remote. Others are conceptually suggestive but technically incomplete. The visible universe does not yet yield its substrate easily. Still, the repetition of the same pressure from black hole thermodynamics, quantum gravity research, holographic dualities, and the persistent incompatibility between smooth classical space-time and microscopic quantum principles is difficult to dismiss as coincidence. The old picture is under strain from too many sides at once. The strain does not prove that space-time is emergent, but it makes the possibility feel less like metaphysical indulgence and more like the kind of radical shift physics has learned to expect when its deepest frameworks begin to contradict one another. If space-time is emergent, then the origin of the universe becomes even more mysterious than it first appeared, but also more coherent in a subtle way. The question changes from how something appears in a void to how a void-like appearance, along with time, law, and matter, crystallizes out of a deeper reality that cannot be pictured using the concepts it later generates. The universe would not be a thing placed inside a larger emptiness. It would be the visible phase of a hidden order, a stable interface through which a more primitive system becomes readable as geometry, particles, and history. The Big Bang would remain real, but as an event inside the emergent phase. Inflation would remain real, but as a process acting after the stage already exists. The laws of physics would remain real, but as the grammar of one settled cosmic state. What would disappear is only the assumption that these are ultimate. In their place would stand a colder and more spacious possibility that everything familiar, from distance to duration to gravity itself, is a local translation, and that the true origin lies not behind the first moment in time, but beneath time altogether. At a certain point, the origin question begins to invert. Instead of asking what happens before the universe, some theories ask whether the universe is itself the inside of something else. This sounds at first like a move away from science and into myth, but the thought grows out of a genuine tension in modern physics. General relativity predicts singularities at both cosmic beginnings and inside black holes. Quantum theory suggests that such infinities are signs of incompleteness rather than final truth. The observable universe expands from an early hot dense state that resembles, in certain mathematical ways, the reverse of gravitational collapse. Black holes hide their interiors behind event horizons, cutting them off from external observers. Cosmology hides its earliest accessible state behind a horizon of a different kind, beyond which direct observation cannot reach. These echoes do not prove that a universe can be born inside a black hole. They do make the idea difficult to dismiss as pure imagination. The equations keep placing beginnings and endings in uncomfortably similar positions. The black hole hypothesis takes several forms, some more concrete than others. In its simplest and most provocative version, a collapsing region in a parent universe forms a black hole, and what appears from the outside as a compact object with an event horizon corresponds on the inside to an expanding space-time region that can behave like a new universe. To external observers, matter falls inward and becomes trapped. To internal observers, if such observers eventually arise, the local reality would not look like the interior of a collapsing star. It would look like an expanding cosmos with its own time direction, its own large-scale evolution, and no observational access to the parent region beyond the horizon. The event horizon would act not only as a prison wall, but as a boundary between levels of reality, one side describing collapse, the other describing birth. This idea is deeply speculative, but it gains emotional force from the strange role horizons already play in relativity and thermodynamics. Horizons do not merely hide information, they reorganize what different observers can meaningfully say exists. There are features of the observable universe that make such a proposal feel at least narratively aligned with known physics. The universe begins in a dense state. It expands. It may have a preferred arrow of time emerging from a highly ordered beginning. Black hole interiors, according to classical relativity, are also regions where the geometry changes dramatically and where conventional intuitions about space and time fail. Inside the horizon, radial direction and time-like behavior exchange roles in ways that already strain ordinary language. If quantum gravity resolves the singularity that classical collapse predicts, then the interior may not terminate at an infinite point at all. It may continue into some new geometric phase. In that case, what appears from the outside as one ending may appear on the inside as another beginning. The symmetry is not perfect, and many technical obstacles remain, but the resemblance is strong enough to keep the question alive. The universe may be less like the whole book, and more like one chapter hidden inside a deeper volume. This thought becomes even more compelling when the status of singularities is reconsidered. If both the Big Bang singularity and the black hole singularity are signs that classical space-time has reached the edge of its validity, then perhaps the deeper theory that replaces them also connects them. A bounce inside collapse is one candidate. Instead of matter compressing forever toward an actual singularity, quantum gravitational effects might generate repulsion or new geometric behavior at extreme densities, halting collapse and redirecting it into expansion. From the perspective of a parent universe, the black hole remains a black hole. From the perspective of the interior, a hot, expanding cosmos begins. This idea appears in several forms across different approaches to quantum gravity and cosmological speculation. None is established. All share the same underlying intuition. Collapse and birth may be opposite faces of a deeper transition that current physics only sees in fragments. There is an intriguing observational subtlety here. If the observable universe does originate from something like a black hole interior, direct evidence of the parent universe may be almost impossible to obtain. The event horizon and the subsequent expansion would seal off most traces. Inflation, if it also occurs, would further erase any earlier irregularities. The result would be a cosmos whose deepest ancestry is hidden twice, first by the birth mechanism and then by the smoothing of later evolution. Yet certain broad features might still tempt interpretation. The ordered beginning of the universe, the low entropy of the early state, and the existence of horizons in both cosmology and black hole physics all continue to press on the same conceptual weak points. Why does the universe begin so smooth? Why does time flow outward from that beginning? Why do gravitational boundaries seem to carry thermodynamic meaning? These are separate puzzles in standard cosmology. In black hole cosmology, they begin to look like related symptoms. The idea of a cosmic bounce offers another route to a universe with a hidden parent, even without black holes. In bounce models, the universe does not begin from absolute nothing or from an actual singularity. Instead, it passes through a prior contracting phase. As density rises, new physics prevents total collapse and redirects the cosmos into expansion. The Big Bang then becomes not the first moment of all existence, but the transition point between contraction and expansion. There are many versions of this idea. Some arise from loop-inspired quantum geometry, where space-time discreteness modifies gravity at extreme density and can produce a rebound. Others appear in ekpyrotic or cyclic scenarios, where large cosmological phases succeed one another and smoothing occurs during contraction rather than only through inflation. Some hybrid pictures combine elements of bounce cosmology with inflationary dynamics afterward. The details vary, but the central move is the same. The beginning is replaced by a turning point. This move has a certain elegance because it removes the need for an absolute origin inside known time. A bounce turns the first question from what creates the universe into what creates the conditions for the bounce, which is not a full solution, but can be a conceptual improvement. It also offers a possible explanation for the smoothness of the universe if the prior contraction phase suppresses irregularities. More importantly, it turns the singularity from a physical endpoint into a sign that classical description must be replaced near the highest densities. This fits the broader lesson already suggested by black holes and early universe physics. Infinities are warnings, not destinations. The universe may pass through conditions where current coordinates and concepts fail, but reality itself continues through the failure. Yet bounce cosmologies carry their own mysteries. What determines the preceding phase? Was there only one contraction and one expansion, or an endless sequence? If cycles repeat, why does entropy not simply accumulate in a way that destroys the possibility of renewal? If the bounce is quantum in origin, what precisely is the underlying structure that survives the transition? And perhaps most importantly, can any of this be tested? Some models predict distinctive imprints in primordial fluctuations, non-standard gravitational wave backgrounds, or subtle departures from inflation-only expectations. But the window for decisive evidence remains narrow. The earliest observable universe has already processed its own history through enormous expansion and thermal evolution. The deeper the prehistory, the harder it is to distinguish from elegant storytelling draped over inaccessible time. This same difficulty appears in multiverse ideas, though in a different form. Eternal inflation suggests that the observable universe may be one local pocket within a far larger inflating structure. String-inspired landscape reasoning suggests that different vacuum states might support different low-energy laws and constants in different regions. If so, the visible cosmos is not the whole of existence but a local realization inside a much broader ensemble. The origin question then fragments. One can ask how this universe begins, how the larger inflationary background begins if it begins at all, and whether the laws observed locally are selected dynamically, statistically, or anthropically from a wider landscape of possibilities. In this framework, the strange suitability of local constants for complexity may not reflect deep necessity. It may reflect that only certain regions ever host observers capable of asking the question. This line of reasoning remains controversial because it can drift toward explanation by selection rather than by predictive mechanism. Still, it emerges naturally once a sufficiently rich cosmic architecture is entertained. What ties black hole birth, bounce cosmology, and multiverse scenarios together is not a single agreed model. It is a shared refusal to treat the observable universe as automatically self-contained. Each proposal suggests that what appears locally as a beginning may be an interior event in a larger reality. The cosmos may be nested, it may inherit conditions from a parent structure, it may recycle through phases, it may branch into separate domains with different effective laws. In every case, the Big Bang loses its role as the absolute first line of all existence, and becomes instead a boundary event whose meaning depends on a broader context. This shift is both explanatory and destabilizing. Explanatory because it gives the beginning a genealogy. Destabilizing because every new context invites the same question at the next level up. If this universe is born from a black hole, what births the parent universe? If this cosmos is one bounce in a cycle, what grounds the cycle? If this region is one pocket in a multiverse, what sets the larger framework? The mystery is not removed, it is propagated upward. There is also a subtle relation between these large speculative structures and the earlier suspicion that space-time itself is emergent. If space and time are produced features, then different universes or phases of reality need not be laid out inside one giant pre-existing container. They may be separate emergent domains connected only through a deeper substrate. A black hole interior birth would then not require a simple spatial tunnel from one universe to another. A bounce would not require time to flow continuously in the familiar sense across the deepest transition. A multiverse would not require all universes to float beside each other like bubbles in ordinary space. These images are useful only up to a point. Beyond that point, they mislead by importing the very geometry whose emergence is in question. The larger reality, if it exists, may be related more like different solutions, phases, or branches of a hidden formal structure than like neighbouring rooms in a cosmic building. This is part of what gives these theories their quiet, disorienting power. They do not simply enlarge the cosmos. They make enlargement itself ambiguous. A parent universe may not be larger in any spatial sense accessible from inside the child. A pre-bounce phase may not be earlier in a way ordinary memory could ever recover. Another vacuum domain may not be elsewhere in a direction any light could travel. These are not failures of imagination. They are the consequences of taking modern physics seriously when it says that space, time, and causation may not be basic in the form experience presents them. The universe then becomes interior not merely in the sense of being enclosed, but in the sense of being one localized appearance inside a deeper order that does not resemble any ordinary outside. Against this backdrop, the idea that the universe could be inside a supermassive black hole no longer sounds like a simple sensational claim. It becomes a shorthand for a broader and more technical suspicion that cosmic beginnings may be generated by gravitational boundaries and hidden transitions in a larger system. The fearsome image of a black hole swallowing matter and generating a new expanding space-time on the inside is vivid. But behind that vividness lies a more careful insight, Gravity, information, horizon thermodynamics, and singularity resolution may all belong to one unfinished framework. If they do, then black holes are not merely dead ends in the universe. They are laboratories of origin, places where known physics reaches its breaking point and hints that creation and collapse might be related processes seen from different sides. Still, no decisive observation has confirmed any of these grand pictures. The cosmic microwave background does not yet plainly reveal a bounce. No unmistakable signature points to a parent black hole. No collision scar from another bubble universe has forced consensus. No theory has unified all the pieces into a single testable account accepted across the field. The speculative edge remains speculative, yet it is not arbitrary. It grows precisely where the strongest theories fail most dramatically. It grows at singularities, horizons, vacuum transitions, and the first fractions of cosmic history. It grows where the observable universe appears too orderly to be fully self-explanatory and too hidden in its beginning to be closed by ordinary extension of current law. Science reaches that boundary and does not stop. It begins drawing possible larger structures around the visible cosmos, not because imagination has run wild, but because the known evidence keeps implying that the whole story is unlikely to fit entirely inside the part that can be seen. In that sense, the most unsettling conclusion of these theories is not that the universe might sit inside a black hole, or emerge from an earlier contraction, or occupy one patch within an endless inflationary foam. It is that any of these could be true while leaving the observable world almost exactly as it is. The stars would still form, galaxies would still cluster, the microwave background would still glow, gravity would still guide motion. Reality could be locally coherent and globally incomplete. The cosmos that is measured might be only the stable interior behavior of a much larger process never directly accessible from within. Physics would continue to work with extraordinary precision, while its domain of ultimate applicability quietly ends at the edge of the local universe. The beginning would then remain hidden, not because nothing lies before it, but because too much lies around it, above it, or beneath it for a local observer to reconstruct from the inside. The universe would be real, intelligible, and measurable, and still only a chamber in a structure whose full architecture remains almost entirely dark. By the time the universe is traced back through expansion, ancient radiation, primordial elements, inflationary smoothing, quantum fluctuations, singular boundaries, emergent law, and the possibility of parent structures beyond observation, the phrase physics could be fake no longer sounds like a crude rejection of science. It begins to mean something more precise, more technical, and more unsettling. The success of physics is not in doubt. The equations guide satellites, predict lensing, describe stellar evolution, explain the microwave afterglow, and reconstruct the early universe with a level of accuracy that would once have seemed impossible. If physics were fake in the ordinary sense, none of this would work. The stars would not obey the same nuclear rules across billions of light years. The cosmic background would not match the predictions of hot early expansion. Black holes would not behave the way gravity insists they should. The problem is not that physics fails. The problem is that it may be too successful in one band of reality and too silent about what lies beneath that band. A map can be exquisitely accurate within a country and still reveal nothing about the mechanism that printed the paper, chose the projection, or defined the borders. This possibility grows sharper because the known laws seem to stop just where the most important questions begin. General relativity describes the large-scale universe until it reaches singular conditions. Quantum theory describes the microscopic world until the gravitational background itself must become quantum. Inflation explains the shape of the observable cosmos, while likely erasing the evidence of anything earlier. Vacuum physics shows that emptiness is structured without explaining why structure exists at all. Cosmology reveals the early universe in astonishing detail while leaving the ultimate origin untouched. Everywhere the pattern repeats. The laws work. Then they reach a horizon. Beyond that horizon there may not be chaos. There may be a deeper order of which the known laws are only the visible edge. Physics could then be fake in the same way a horizon is fake. It is not unreal. It is a genuine feature of experience and measurement. But it is also not the thing itself. It is the appearance produced when a deeper system is viewed from inside a certain regime. That thought changes the tone of the entire cosmic story. The universe no longer looks like a final machine assembled from the smallest parts now known. It looks more like a stable interface. Space may be an appearance that emerges when deeper relations become geometric. Time may be an appearance that emerges when change can be ordered in one dominant direction. Gravity may be an appearance that emerges from informational or thermodynamic behavior below the level of smooth space-time. Quantum fields may be appearances that emerge from a more primitive substrate not yet adequately named. Even the constants of nature may be local settings rather than timeless absolutes. Nothing in this picture makes the world illusory in the simple sense. The stars are not less real because nuclear physics might be emergent. Black holes are not less real because horizons may encode hidden microstructure. The universe remains physically real. What changes is only the claim that its currently visible rules are ultimate. This is why the question of nothing becomes so treacherous. If every time reality is stripped to a supposed foundation, another layer is found beneath it, then absolute nothing may be less a physical possibility than a limit of language. The vacuum is not nothing. A quantum state is not nothing. A pregeometric substrate is not nothing. A law-bearing mathematical structure is not nothing. Even a parent universe hidden behind an unreachable boundary is not nothing. Again and again the origin question is driven downward, and again a subtler something waits there. The universe may never have come from nothing in the strictest sense because strict nothing may not be available to nature at all. It may be a concept formed by minds living among objects, then mistakenly extended into domains where objects, places, and moments do not yet exist. The beginning would then not be the conversion of non-being into being. It would be the emergence of one level of being from another more hidden one, perhaps with no final empty floor beneath the entire stack. If that is so, then the deepest mystery is not how the universe cheats nothing. It is why reality has layers at all. Why does one regime emerge from another? Why do lawful surfaces appear above hidden substrates? Why do the emergent levels preserve such stable regularities that they can mistake themselves for the foundation? Why does the observable universe carry a beginning that looks mathematically simple and physically fertile at once? Why does it arise with a low entropy order that allows time to run outward into complexity? Why do quantum fluctuations grow into galaxies? Why does empty space carry energy? Why do horizons carry entropy? Why does geometry behave as though it is statistical? None of these questions defeats physics. They surround it. They suggest that the known laws may be middle-level truths, enormously powerful but positioned between appearance and source, rather than at the final source itself. This layered view also changes the meaning of certainty. In older pictures of science, certainty increases as one approaches the elementary. Smaller means deeper, and deeper means more final. But the story of modern physics keeps resisting that neat descent. The microscopic world is stranger than the macroscopic one, yet not obviously more complete. Quantum mechanics is more fundamental than classical mechanics in one sense, yet may still be emergent in another. Space-time geometry is more fundamental than Newtonian force, yet may itself be emergent from entanglement, or something even less intuitive. The beginning of the hot Big Bang is more fundamental than the history of galaxies, yet it may still be a late event relative to inflation, or to an earlier bounce, or to the birth of space-time itself. Finality keeps retreating. Every level reached with confidence turns out to be a threshold, not a floor. The universe appears arranged in nested descriptions, each one accurate within its domain, none obviously absolute. There is a quiet danger in this thought. One could let it drift into vagueness and say simply that everything is mysterious, that the laws are only appearances, that no firm knowledge is possible, but that would betray the evidence that leads here. The remarkable fact is not that science fails. The remarkable fact is that science succeeds far enough to reveal the specific places where its own categories begin to break. The cosmic microwave background is real. The expansion of the universe is real. Primordial nucleosynthesis is real. Black hole thermodynamics is real. Quantum vacuum effects are real. Theories of inflation, bounce cosmology, holography, and emergent space-time are not interchangeable fantasies. They are structured attempts to account for tensions that appear when these real things are brought into contact. The mystery is disciplined. It is not darkness replacing light. It is light reaching an edge and discovering that the visible surface of reality may be thinner than expected. In that sense, the possibility that physics is fake becomes less an attack on reason than one of reason's most mature conclusions. A successful description does not guarantee ontological finality. The laws that work may be effective laws. The symmetries that seem primordial may be the frozen outcomes of earlier transitions. The constants that appear fundamental may be environmental or emergent. The beginning that appears absolute may be local. Reality may still be governed, measurable, and coherent, while the governance belongs to a deeper architecture not expressed directly in the equations used now. This is already familiar in lesser forms throughout science. A gas obeys thermodynamic laws that conceal molecular chaos. A crystal obeys elastic laws that conceal lattice dynamics. A computer display obeys visible interface rules that conceal electronic states beneath. In each case, the surface description is real, rigorous, and incomplete. The startling possibility is that the entire observable cosmos may stand in the same relation to a hidden substrate. That would explain why the universe seems at once intelligible and withholding. It gives enough order to support science, enough regularity to support prediction, enough continuity to support mathematics, but not enough transparency to reveal its own source directly. The cosmos may be built to be knowable from within only up to a point, not by intention, but by structure. Observers inside an emergent regime may discover the laws of that regime with astonishing success, and still remain largely blind to the generative layer beneath it, just as creatures confined to the motion of waves might infer wave equations, while never directly seeing the molecules that make the water possible. The visible world would then be neither deceptive nor complete. It would be a readable surface whose consistency is real precisely because it is emergent from something deeper and more stable than the surface itself. This makes the universe feel stranger than a simple creation from nothing. A creation from nothing is at least compact as an idea, even if impossible to picture. A universe built from stacked layers of emergence, erased prehistories, informational boundaries, hidden vacua, and local laws masquerading as absolutes is harder to hold in one thought. Yet it may fit the evidence better. The cosmos is not merely born and expanding. It is born from a beginning that appears increasingly indirect. Its first accessible moments are already post-transition. Its visible laws may already be late products. Its smoothness may be the result of inflationary erasure. Its structure may come from quantum irregularity. Its geometry may come from something more abstract than geometry. Its apparent totality may be local to one bubble, one bounce, one interior, or one emergent phase. The universe then is not fake as an illusion is fake. It is fake as a mask is fake, not false, but not the face beneath it. And this may be the most faithful place to stop. The evidence does not compel one final story. It compels a narrower and more demanding honesty. The observable universe has a real history, but the ultimate origin of that history is unresolved. The Big Bang is well supported, but it may describe the aftermath of an earlier event. Inflation is powerful, but it may conceal what it depends on. The vacuum is active, but it is not nothing. Laws are stable, but they may be emergent. Space and time feel fundamental, but they may be phase properties of something deeper. Black holes may be endpoints, or laboratories, or gateways, or all three in different descriptions. Every successful explanation opens a more difficult background question. The mystery is not that science knows too little. It is that the more it learns, the more reality begins to look layered, local, and unfinished from the inside. If the universe comes from nothing, then nothing may not mean what it seems. If physics could be fake, then fake may only mean that the deepest truths do not look like the rules visible on the surface. And if that is the case, then the beginning of everything is still out there, not only in the far past, but hidden beneath every law that continues to work with perfect calm across the sky.